Good morning. I'm Nudrat, a rising junior at Orangeburg-Wilkinson High School.
I'm Alexis Dowling. I'm a rising junior at Orangeburg-Wilkinson High School.
Good morning. I am Crashaida, a rising senior at Edisto High School.
The title of our project is Measuring the Effectiveness of Antibiotic Ligands on Gram-positive and Gram-negative bacteria, and our initiative remark is 3.
We are basically trying to synthesize the carbonyl-ferricene derivative using ciprofloxacin and ampicillin to fight off bacteria. And so we're trying to find the acetyl chloride based off of those properties.
Okay, antibiotics are used to treat a wide range of infections caused by certain types of bacteria. And 9 times out of 10, someone in here has went to the doctor and has to have an antibiotic to kill their infection. Well, antibiotic doesn't work alone to kill your infection. It is mixed with an acetyl chloride. And the acetyl chloride that we use is chlorocarbonyl-ferricene. So, and chlorocarbonyl-ferricene is priced at $300 per gram. And we're trying to replace chlorocarbonyl-ferricene with 5-bromo-carbonyl-pyridine chloride, which is priced at $132 per gram.
And this is our ampicillin structure, which is a part of the penicillin class that treats infections by killing the bacteria that are responsible for the infection. Okay, ampicillin is works by killing sensitive bacteria by inferring information from bacteria while it is growing, mainly used for urinary tract infections and chest infections. Penicillin is a part of a group of antibiotics that is produced naturally and usually treats skin infections, dental infections, and sexually transmitted diseases. Ciprofloxacin is a fluoroquinolone. The difference between a regular quinolone and a fluoroquinolone is that the fluoroquinolone uses a fluorine atom, while the quinolone does not. And ciprofloxacin, like any other bacteria, helps with chest infections and infections in the digestive system, so forth. And we use both gram-negative and gram-positive bacteria. Our gram-negative was Pseudomonas aeruginosa E. coli, and our gram-positive was Staphylococcus epidermidis and Micrococcus lupus. And this is our 5-bromo-carbonyl-pyridine chloride, which was made at Cleveland. And the reason why they call it 5-bromo is because it attaches to the 5th carbon.
Okay, so during our experiment, we used the disc assay, which we used a petri dish and we cultured our bacteria on it, and we put a filter paper on it, and we put our 2 ligands on it and our control variable, which was methylene chloride, and we tested it to see if it created ozonic inhibition. And ozonic inhibition indicates the degree of sensitivity of bacteria to a drug. Okay, the shrink line. We use this to synthesize our ligands, and this knob right here, when you turn it to the right, nitrogen comes right here, and it condenses the liquid, and we turn it to the left for 24 hours, and the vacuum sucked out all the excess vapor. And this is our ampicillin ligand. This is our 5-bromo-carbonyl-pyridine chloride, and we added to ampicillin, and these are 2 solvents, methylene chloride, and right here is pyridine. And this is our ampicillin ligand. This is where the bonds is a bond, and the petal bond, and the nitrogen connected to our proteins plus HCl.
Okay, so this is the molecular weight of the ampicillin complex, and as you've seen previously on the last slide, that there is the figures. So the figures always have math equation to it. So over here, the 5-bromo-carbonyl is 220.05 grams per moles. The ampicillin is 349.41 grams per moles. And ampicillin ligand is 533.01 grams per moles, and hydrogen chloride is 36.45 grams per moles. And in order to find our ampicillin ligand, you have to add up 220.05 grams per moles plus 349.41 grams per moles subtracted with 36.45, and you get the product of the ampicillin ligand, which is 533.01.
This is our ciprofloxacin ligand. This is the 5-bromo plus our ciprofloxacin and our methylene chloride and our pyridine, and this is the ciprofloxacin ligand plus our HCl.
Again, it's the same thing, but this time it's the ciprofloxacin, where it has a 331.35 grams per moles of molecular weight, and you exchange it from what you had, and you get 514.95 grams per moles for the ciprofloxacin ligand.
So the methods we used during our experiment, we prepared our ampicillin and ciprofloxacin ligand, and also we used a diffusion assay. So we combined 150 milligrams of 5-bromocarbonyl chloride with 238 grams of ampicillin, and we also combined 150 milligrams of 5-bromocarbonyl chloride with 230 milligrams of ciprofloxacin, and we combined both compounds together with the addition of methylene chloride and pyridine because the compounds can't mix until they're broken down into the simplest form, and our solvents did that. And we allowed the reaction to go for 48 hours under nitrogen in a warm water bath. The reaction was then put under the shrink line for 2 hours, which mixes our ligands together. And the MR analysis was done before and after the reaction. And we prepared the media in a bacteria place, including our specified bacterium, and we proceeded to do this diffusion assay by using 0.5 milligrams per milliliter per disc, using methylene chloride as our control, and the plates were incubated at the temperature of 25 degrees Celsius for 24 hours and stored in the refrigerator at the temperature of 7 degrees Celsius for 24 hours, and the zones of inhibition were then measured for each disc for each bacteria.
So as you can see, this is the results of what we were doing. Over here, it is the refrigerated result, and it is 7 degrees Celsius. As well as over here, it is 37 degrees Fahrenheit. And these are the zone of inhibitions, where you see if it has greater effects or not. So over here is the data of our previous experiment and our current experiment. And as you can see, ampicillin had greater effect on E. coli, and Pseudomonas is the one, aeruginosa, has the same comparable result from ciprofloxacin and percentile yield. So in order to find our percentile yield, we have to go and find our theoretical yield. And our theoretical yield for ampicillin was 0.368, and ciprofloxacin was 0.355. And in order to find the ampicillin, so we had 0.110, which is our actual yield from previous experiments, and you divide it with 0.368 times 100, and you get 30% of that. And ciprofloxacin is like 0.250, and then divide it with 0.355, and then you multiply it 100, and you get 70%. And I know it's a lot of math, and there's a lot to go with it, how we found the theoretical thing, so you guys have to, if you guys want it, I'll do it later. If you guys want it, it's not. So in conclusion, so we found that ampicillin is a better substitute for our enoxacin, which was our previous product. So it worked better on E. coli, and we found a better comparable substitute for aeruginosa by using ciprofloxacin ligand. So as our result showed, the 5-bromocarbonyl chloride did work, but it was not as effective as we hoped for it to be. But, you know, for a cheaper product, it did have an effect, even if it wasn't strong enough. And I feel like that what we were doing, we were only doing it for like 2 weeks. So for that to be our result, it was pretty cool. For future works, we're going to, next step is to do the research, fully analyze the ligands in the Nawar, and also we would change up the ligands and put it on other bacteria, because there's not only just 4 bacteria, there's more than that. So we would like to see if ampicillin and ciprofloxacin actually works on other bacteria that there is out there. And these are our references.
We really appreciated the opportunity that we received to participate in this summer research camp. The experience we have encountered in the Epscor program was miraculous. We would like to thank Ms. Cherry, Mr. Curry, and Mrs. Azima.
Kayla Scott, Kiana Ware, Edwin Simpson,
Dr. Tisdale and Dr. Peters.
Look at the equipment at NMR
Yes,
machine
ma'am.
that you would put it on at the next step.
Yes, these are the proteins for what we were using, so that was like different. It was complicated.
What is that?
Magnetic
Resonance.
So over there, you put in your compound in, and then you see if it has proteins and all those.
it basically tells the chemical makeup of an organic compound.
You mentioned what the Schnick line does, but you never said what exactly you use it for in your project.
We use it to combine them.
So she left them together.
Yes, ma'am.
One is ciprofloxacin, right? So which one you found is more effective? Yes.
A ciprofloxacin ligand.
And secondly, ciprofloxacin is a group of fluoroquinolones which are broad spectrum. What do you mean by broad spectrum?
They're derived from an actual antibiotic. What?
This experiment, and we had to have, like, you know, compared to apples, and not necessarily